We have a really awesome class, and the reason we have an awesome class because as I talked before, the experiment, and the one of you that didn't saw, I'm going to put a link to the experiment down below so you can see it also as well. And the experiment we learn about resistors, okay? And till so far we covered voltage and potential, which was energy, supply of energy that we have, and then we learn about capacitor. How can I accumulate this energy and use it whatever I want, right? And now today we're going to learn about the most interesting stuff, which is resistors. Why this is so interesting? Because think about it, that no matter how much money do you have or how much energy do you have, the really interesting stuff is, to waste it, to use it, to do stuff, right? Fly abroad, do something cool, buy something nice, use the energy to do something. So today I want to give you a little bit more practical example, that you can use in your startup, in your ideas and stuff like that. So I actually brought with me some resistor, which is this one, okay? The camera can do a zoom inside the thing. Where is the cameraman? Nice. Yeah, you wake up? Can you see it? Wait. Can you see it? So this is the kind of the sticker resistor, really cool. So you can pass it between you to see it. And the name of this device is actually called strain gauge, okay? And you're gonna see it in a more, advanced classes. And I'm sure you're gonna use it and you don't know, but you already have used it a lot of times. It's really, really cool thing. So let's write it down. So this one called strain. And what is the definition of the word strain? You know? What's the definition of strain? Changing length. Yeah, there's many things to look at it, but it's kind of changing in length, right? So kind of deformation in length. I think it's a better word. And the second word is gauge. You know what is gauge?
Something to measure.
Measure or counting, right? So strain gauge, this is the device. And the device is actually a sticker that you can put on stuff, and it tells you how much this thing shrink or actually extend. Okay, that's the idea of this sticker, and it's based on resistors. So before we're gonna start, I'm gonna do some, some basic questions. So our first question, let's call it 1A. 1A. It's gonna be, what is the resistors? What is the resistance? What is the resistance of some really simple resistor, this kind of shape, rectangular, right? Okay, so the formula to resistance, which is this one, I have a method to remember it. You don't have to use this method, but for me it's working. Resistance, I think about it as something really sad. You need to resist, you need to do this. So I'm drawing a sad smiley. That's what I do, a sad smiley. And then I'm making this one A, this one L, and this one rho. This is my method. It's stupid, but if it's working for you, perfect. What is each one of them present? Okay, so L is actually the length of my resistor. Okay, let's do it in a different color. Let's see if I got blue. Perfect. So L is the length. And I really love to use the metaphor of thinking about driving. How much resistance do I have if I want to drive this road? Okay, if I'm some car or child, this is the analogy, and I want to ride this road, if it's a really long road, for example, from Haifa to Eilat, it's really long road. I need a really big motivation to drive all this way, okay? So I have a lot of resistance. You see it? What is A? A is this area. Is if I'm the charge and I'm coming to this material, okay, this is some material, it can be copper, it can be wood, it can be many things. So what is the area that they're gonna see? And in my car analogy, I can think about it, how much, passes that I have. How you call it in English? On the road when you have this one, and this pass, and this one, and you can change them, how? Lines. Layers? Lane. So I learned also a new word, lane. So if I have many lanes, so if something wrong going here, I can move to the side or here. So this is actually make my resistance go low if this increase, right? So it's a good road. I have many lanes to go, perfect. And the last one, which is really important, is the material property. Note, it's not the charge density, okay? It's this one, is resistivity. Resistivity. And it's how much this material resists to a current going by. For example, in our experiment, what we had here wood, right? And it was such an enormous resistance that charge cannot go into that. It was too hard, too huge barrier. It's like L. L is a huge barrier. If I'm gonna increase the energy that I try to push this charge inside, for example, thunder lighting, which you have a huge difference of voltage between the sky to the ground, so you actually can pass this one. It can happen, but you need to put a lot of energy, okay? But when we wet the wood, what's happened to the wood? It changed its material property. It changed this guy, and the resistance dropped down, and we can pass charge into it. That's clear right now, what we did outside? So this is the formula, super important, okay? Star for importance, okay? Perfect. So let's draw, okay? I'm moving to this wall, okay? So cameraman, join me. So I'm gonna draw how the sensor, what? Yes?
What is strain gauge?
Strain gauge is the name of the device that I just brought to class, okay? It's to you to see, which is an example of a resistance. Great question, because right now I'm gonna draw how strain gauge look like. Okay, so strain gauge is actually have this form. It has some voltage here, which I'm buying a battery for my sensor, right? And it's connected to a resistance, rectangular resistor. Here it is. And this one continue and connect to another one. And this one continue and connect to another one. And this one to the last one. Connect and go back to the battery. Okay? Each one is a resistor. With the length L. You see it? So this is our device. Okay? So my question to you is, what is the equivalent resistor of this circuit? Remember we did that on capacitors? Remember? So what is actually our total? Okay? The equivalent resistor that can play the game of all of these resistors. If I'm gonna take out all the resistors and put this resistor, it's gonna give you the same game, okay? The same phenomena, electrical phenomena. So how does resistors connect to each other?
They're in series, right?
Exactly, they are in series. I draw it like to make it confuse a little bit. I really love this example. So what is actually a resistor? Resistor is that one resistor, let's imagine this is the hand, one resistor holding, you know, the voltage. And the other resistor actually touching another resistor, and another, and the last one, what? Touching the battery. So there are actually only two ones, the end one that actually touching the battery, and all the rest are connecting to this top and bottom one, okay? The last and the first, okay? And they actually fighting about this battery. They're fighting about this voltage, okay? They try, I want it, no, I want it. No, I want all the energy. No, I want all the energy. So they need to decide how the energy gonna split between each other, okay? So if we have parallel, what is the parallel? If it was parallel, actually, this point was connected to some resistor, right? And this one, wait a second, that's it, okay. So resistor, and another resistor was connected to this line, right? And another resistor, so here, everybody are the kings. Everybody getting the full battery. There's no fighting, only hugging and love, okay? That's what's going on here. So let's continue with our example. So we ask, our second question is, what is the equivalent resistor? This is our total, so it's 1B. Let's call this question, okay? So we said that we know they are in series, right? So I want you to know that if we want to do something in series, so how are we gonna sum them up? we're gonna just, so to sum each resistor. That's the formula, and I want you to note, it's the opposite way of capacitor, remember? In capacitor, this was parallel, okay? So a method to remember is remember that resistors, okay, resist what's happening in capacitor, okay? That's what you have. So what actually we have here, let's draw it right here. Cameraman, you with me? You see me? Yes, perfect. If you're okay, good. So our total, in our case, equal to the first one plus the second one plus the fourth one, the third one, plus the fourth. And here I want you to leave empty space, okay? We're gonna discuss that. Okay? So what is the first one? What is the formula? What is the formula? Okay, length, right? The length of the resistor. And
Resistivity divided.
you'll have the effects. See it, the effects. Okay, and A, the area that I see. And last row, which is the resistivity, which is not charge density. I know I would suggest to do a Hebrew letter here, okay? But you know that we have the English and the Greek letters, okay? And we have also the charge, the resistivity, okay? So they all the resistors in this strain gauge are the same, okay? So we're actually gonna have this how many times? 4 times, right? This and this.
They'll be different lengths.
No, they have the same length, that's how you buy it. Okay? So we actually put here, okay, here is something actually. And so we actually gonna get this term. Everybody have the same row A, but we have 4 times this thing. That's the way I love to write it. Why? Because when you sum up resistor, what you're actually doing to the road, you extend the road. That's what's going on. Okay, so when you want to, if you have, for example, an electrical circuit, and you said, gosh, I need more resistance, okay? It's too dangerous, okay? I need more resistance to take some of the energy out of the system, okay? So what you're gonna do, you're gonna add capacity, you're gonna add resistors, okay? You understand this concept as a startup man, right? That's the idea, that's what I want you to have in mind. So the last thing I want to talk about is that someone of you, that's what happened to me in the other class, said, but Ron, wait a second, I think you kind of trick us. I see another resistor in the system. Do you see it? Somebody that has some length, area, and material property. Is the wire. So look at the wire for a second. The wire is short or long? Is huge. Look at the scale. Okay, so we actually have, this huge L, right? And what is the area of this? Very small. And this is where it's down below, so it's actually increasing. So tiny. So this number should be huge, but we didn't talk about someone. Who is it? Resistivity. So if I'm gonna take, for example, copper, which is a common use, things for wiring, or gold. So what is the value of copper? So I'm gonna write it below. It's actually equal to 0.000000171. So what this term actually did? It's killed it, right? It just killed it out, okay? So actually, I agree. Completely fair question. Why I didn't put the wire inside? Because the wire is so negligible. I give you this example last time. If I'm gonna go and weight myself, how much I weigh, so I'm gonna have a number. And if I'm gonna go to have a haircut and come back, this is not gonna affect too much. I agree, I lost some weight, right? I took a haircut. Okay, so these have some weight, but it was not relevant in the scale. And this is something that I really want you to have as an engineer, this intuition, okay? Because the idea of to be engineer is to see where the stuff that I can neglect, forget, and get to the solution and solve the problem, okay? Do the new things, okay? Have the idea for the medical startup, have whatever you want, okay? So this is the idea. So now we found out what is the equivalent resistor of this circuit. So now something really cool that I want to share with you is to ask what is actually the current in this circuit. Okay, so I'm gonna clean this thing. So let's do it. What is the current I in the circuit? Okay, so to solve this problem, we have a nice formula which is called Ohm's law, V equal IR. Okay, and I want you to read it. How it sounds like? Read it. VIR. Vir sounds a little bit like what? Like beer, right? So if you want a method to remember this formula, that's a fine, stupid method. Love it, adapt it. Don't like it, forget about it. Okay, so that's I always call it the beer formula. Okay, so beer law, that's how I call it. And what this is actually saying. So V is the voltage, is how much I try to push this charge to go and travel on the wire and on the resistors. Okay, that's what we're trying to do. If I'm gonna put a lot of voltage, it's gonna go really fast, right? We're gonna put small, it's maybe would not be enough even to push it, to start the thing out, okay? And what is R? R is how much I want to stop this charge from moving, right? And stop sign, okay? How much I want to stop them from moving on. And what is I? I is actually how much they are moving. So the definition for how much the charge is moving is dq, small charge, dt, which means in a unit formula, it's how much coulomb do I have that pass through in 1 second. So think about that, okay? We are in slow motion right now. I'm standing on the wire and I see some charge, electron. Choo, 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 choo. And 4 pass by in 1 second. I stop the timer, okay? I say, okay, so if 4 charges pass in 1 second, this is actually 4 this stuff. Actually, sorry, not electron, but coulomb. Okay, 4 coulombs pass by in 1 second, so I know how much I have, how much current do I have in my wire. Okay, this is.
What do you mean by beer?
What?
What do you mean by beer?
Beer, like waking up, you know. So what I mean by beer is a method to remember this formula. Okay, beer sounds like beer. Got it?
It sounds like what?
Beer sounds like beer. Beer is like reading the equation. Okay, VIR. Okay. So good. And so this unit, we have a special name for them. I don't love the name because the letter is A, and A I love to area, right? So, but you need to be a little bit careful about it. So this one is Ampere, okay? And it's after a scientist named Ampere, okay? So we're gonna learn his idea later on in the class, a really smart guy, okay? So how are we gonna find the current of the system? We just found what is the resistance of the system, and we know we bought the battery, we know what the energy we put inside, right? So I'm gonna clean this board. So if I want to find the current, so the current equal to what? I equal to V divided by R. Got it? Okay, so this is given, right? Given, and R we just found it was the length, row A, and 4 times the length, since we have 4 resistors which are the same, and we end up with having this A for L row, and this unit is actually ampere. So we just find the current. Perfect. So now something really cool gonna happen, and this is the idea of this resistor. Can you bring me back the resistor? Where is it? If I try to steal it, okay, being noted, I'll be going to be more careful with you. So if, for example, I want to test something, okay, let's say whatever you want to test. something that you want to test how much it extends or shrink. Example, something for your life.
Metal rod.
Metal rod, it's too general. Let's do an iPhone. Okay, I bought the new iPhone and I have a YouTube channel and I want to see if this iPhone is stronger than the previous one. So I take this sticker and put it on the iPhone and take it in my car, okay, and try to go over this iPhone and see if it's extend or not. So I put this strain gauge on top of the iPhone and what I see is this. Look, this is a resistor. I'm going on with my car and I smash the resistors, right? What I did, let's do it again. So actually what's happened to the resistors? The length changed. So if the resistor was until here, so right now, whoop, they become longer, right? Whoop, whoop, right? Here it is. And this one connected to this wire. Okay, so what happened? It was...
We can't see.
The cameraman, they say they can't see what's going on. Okay, so this one was small L. So the new distance, the new length, I'm gonna call it capital L, which is bigger than the previous one. You see it? Perfect. Okay, so my question to you is, what is the new resistance? The resistance definitely changed. Right, before I had to drive from Haifa to Tel Aviv. Now I need to drive from Haifa to Elat. Different distance, okay? So let's clean here and let's try to solve it. So what is the equivalent resistor equal to? Guys, it's your time, it's your class, I'm here just to help, so use your time.
The new length multiplied by the resistivity times.
The new length, perfect, which we know, we can measure it, right?
Yeah.
And we have also which change? The material changed.
Yeah, and the cross section changes too. So
yes, so what happened? If this changed, the length changed, so it should come from somewhere, right? There's no material that show up suddenly. Okay, we didn't do some chemistry experiment. We just smashed this thing, right? Just go with the car over the iPhone. So actually we have here some new area. Let's call it small a. Why? Because if this was that, then a smash it becomes smaller. So we actually need to find this guy. And sorry, it's one N. It's actually 4 of them. 1, 2, 3, and 4. So let's put here 4, okay? And just to remind you that this was in series, okay? In general, you need to sum all the equation, right? You need to sum, and you see me in the camera? You need to sum, Li, and rho I if material is changing, and also AI if the area is changing. That's the idea. In our case, it was only length that's being accumulated. Okay, so
why is it small a?
What?
Why is it small a?
Why is it small a? It's small a because when I actually extend my resistors, okay, think about it, that you have some material, okay, and you start to pulling it out. So where this coming from? All this volume, new volume. It's coming from shrinking the first one that we had, right? Material didn't show up suddenly, it's coming from somewhere, right? So how we can find this A? Exactly what I said. I know that in the beginning, there was some volume, let's call it I initial, okay? And it must be, no volume disappear in the process. It must be equal to what? To the volume of final, okay? And what is the volume at the beginning? A multiplied by L, right? And what is the volume at the end? A. So we actually can get our A outside. So it's actually A multiplied by what? By L divided by L. And this makes sense. What does it say? Say that this is the original, what you have at the beginning, and this is a correction factor, what's happened to it, right? This is without unit, you see? So the original one divided by the big one. So this is actually less than 1, right? This is, sorry, was right, less than 1. So it's actually, I know it's shrinking. Got it?
But small a is also surface?
Yes, of course. A is the surface, this one is this surface.
It's
Surface
confusing
that
because
the resistor, the charge C when it's coming to interact with the resistor. Okay, got it? Perfect. So let's clean this one. So we found the total resistance, and what I want you now to find out, what really interesting me? The current, right? So actually what's really happening is that usually in the circuit, I'm gonna put here a device which calls ampere meter. And what does ampere meter says? Ampere, it's what we are measuring. Meter, it's meant to measure, ampere meter, right? So I'm gonna put this device here, and I think about it as somebody that's standing, you know, like the guard in a club, standing, going, 1, 2, 3, and it's counting how much charge go in 1 second. And it tells you the number. That's what ampere do. Okay, ampere meter. And perfect.
Ron, there's a problem. The video is mirrored. It's not like
All the time it was mirrored, and you didn't say anything?
no, it's only here. Like,
Okay, perfect. So the TV is mirrored, not there. Okay, perfect. Not nice. I'm gonna punch you at the end of the class. Okay? So you need to compensate, okay? And so the question I want to ask you right now is, as you have initial resistance, what we have right now at the current, another current, the final current. So, okay, so we're actually looking for, this is 1 watt, 1 D. This was 1 C, I think. So this is 1 D. So 1 D is what is I final. Now we can find I final. Which formula?
Beer.
The beer, okay? So we can use what I call the beer formula, the beer law, which is Ohm's law, okay? And I final equal to the voltage, which was all the time the same battery. I didn't come and change the battery and run away. It's never happened, it's the same. And resistors actually changed, right? What's happened to the resistor? This one increased, this one decreased, so I don't know what is the ratio, but something happened there. Okay, so it's V0 divided by this term, which is full L rho divided by A L, and this is jumping out. So this is actually equal to A L V0 for rho L squared, right? This is, what is this one is? The final, what? I don't know, it really depends on geometry. It depends if this was, you know, something that was good for the current or bad for the current. But if you change, this value is not the same value that we got, right? It's a different one. So what is the change in the current itself? I have this one all the time. So we actually can find it. What is the change in the current? We know that the device is going to tell us, dude, just letting you know that before we have something else. Now we have this, but before we had this. And this one we found, right? It was A V0 for rho L. And this one, we just found it right now. It's this term. It's A L V0 for rho L squared. And if I'm gonna do it right, I'm gonna have the I here. And outside, I can pull this term, V0 for rho L, and L squared divided, small l divided by L minus 1. And this one is like this, okay? So this is the term. And what I want you to see, which is really cool, rho, I know it. Okay, I choose the resistor, which material, copper, whatever I want, I can choose it. The length at the beginning, I know, yeah, I'm the company, I decided which length I'm giving you. Voltage, yes, you buy a battery and put it. A at the beginning, you know, yeah, like L, I designed it, I did whatever I want. So the only thing that I don't know is this one. What is the new length? And what is this? This tells me the ampere meter. So what this device actually is doing is telling me how much this stuff is extended. This is formula with only one variable, right? The length, the end length. Okay, got it? I don't need A, the small one. I don't care about it. I can use the big L. instead, right? So this device, this nice device can actually tell you stuff. You can put it on a live tissue, I don't know, and on a whatever you want, and you can actually measure and count how much does it change. And you're actually not familiar with this, but you actually use it a lot of time in your life. Think about, let's clean it. Think about when you're standing on a weight device, for example. If you have a weight device, so it's actually a stage of a spring. There's some spring and you're standing here. Okay, let's do you. You're really proud and you weight, okay? Okay, you're standing on it and you have some mass, right? You have some mg and you're not accelerating anyway, so you're actually standing in place, no acceleration. So this is equal to k delta x. And what is delta x? It's changing length. It's L minus L, right? And this one gonna be, you know, the equilibrium of the spring. So you actually can know what is your weight. You know, K L minus L divided by G, okay? So your measuring device, okay, weighting device, is actually based on this idea. You put a resistor, you see how much you drag these resistors down, and they did an amazing startup, telling how much you weigh using a battery, and that's it, done, okay? So that's the idea of how the device works. And what we know that if we're gonna put a battery inside the device, eventually the battery gonna die out. Somebody actually was taking the energy out of the battery and spread it somewhere, right? That's what happened, conversation of energy, right? So energy, if the energy gets lost, it goes somewhere. Okay, so what actually happened when you have a current, this is I, this is like the current is flowing somewhere, this is the charges, the passing by, they actually transmit energy to the surrounding. And that's the idea of a resistor. When you go inside a resistor, it spreads energy to the wall. It could be, for example, heat. If you have a pan, you know, on a stove device or oven, so the resistor actually producing heat. So the energy is getting lost by that. Or another example, if you have some, I don't know, amplifier, okay? So it's amplifying the sound, okay, to make you hear it. So it's actually vibrate or something like that. Or many things, okay? A light, okay, it's a resistor. The light in your car is a resistor. It gets really hot and getting super hot. It's melting almost. And when actually the light is not working, what's happened? It's melt all the way. It's split. It becomes so hot and so thin that it actually breaks down. It's not holding itself anymore. Huh?
That's when the fuse goes up, right?
And you have a resistance. You actually see it. A resistor that actually broke apart. Look at the car, okay? I can give the car a bulb of a car to show you it, to show how resistors look like. It's the same thing that you have in the device. So what I want to ask you is, you know, I don't care about talking about energy. This is not interesting, okay? Or also volt, you know, I don't care about talking about volt. It's like saying, you know, Bill Gates earned $17 in a second. Oh, so it must be really rich, right? Because every second go by, he earning $17. So we're not really care about talking about energy or voltage. We're actually interesting about talking about, you know, power. How much energy per second I earn or are losing, okay? So the next question that I want to ask is, what is the power of the strain gauge? Okay, so let's clean it. So what is, we are right now with 1E. What is the energy per second? I have to think about energy as a money, okay? Because it's a resource, like money, it's the same thing. So how much money I make per hour, per second, right? So how much energy I make per second is actually called in physics how? Power, which is really a bad name to call it power. I don't like the name. In Hebrew, we have a better name, which is called spec, which means how much did you succeed doing this thing, how much you accomplish. Okay, so in Hebrew, it's a better word, but never mind, we have power. So sometimes in English it's better than Hebrew, sometimes Hebrew is better than English. Ladies, you know the advantage to know languages. Okay, so power is actually how much energy, work, I have in a second. This is the definition from Physics 1. So we actually know the energy. We learn about it, right? In the potential class. What is the connection between potential and energy? It's who is the, the person that actually taking care for changing us from energy to voltage is Mr. Charge, right? So Mr. Charge is actually the one that connects energy to voltage, right? Okay, so I wanted to ask you something. Is the voltage in our problem is a constant? Yes, it's a battery that I bought. My money, right? So nobody changes, so I can pull it out. V0 dq over dt. Hey, you know this guy? Who is this one? Is the current, exactly. He's how much charge passing in every second, right? So this term is actually VI, okay? And I love to think about that, oh, you have a lot of power, good for you. Let's give you a V, okay? This is my stupid idea, how to remember. I love remembering formulas by the heart, okay? Because then I'm not, a needy person that, oh, I need to look at it. I just look at a product, think, yeah, this one is this one is this. This makes sense. And you know what? I got an idea. Let's do that and that. So you have a really advantage on other people, especially when you go to a job interview and they ask a question and they see that you actually know it by heart. So and it's not happening in one day, It's accumulating during the degree. You are gaining a lot of information. But if along the way you're gonna start memorize and find tricks how to remember formula, I promise you it's gonna pay off. Okay, so this is the reason I'm more that kind of guy, because I really want you to succeed, to be a manager, to have a startup, to have an awesome idea and give it to the world, give the world the value back, okay? So power is equal to V, and this is the general formula. Of course, we know this one, where it's a constant, and we found this one, right? So this is how much energy I'm throwing to the wall, is joule per second. I have to think about it as like this, okay? Joule for everybody, joule, okay? So this is the idea. That's what actually power is. It's like in every second, how much joules I can throw into the space, right? That's the idea. In the form of heat, in the form of light, in the form of whatever you want, okay? Perfect. And good, okay? We covered that. Notice that if I'm gonna put everything here back in place, so I'm gonna have power equal to V0 square A 4L rho, okay? And if I'm gonna design my strain gauge in such way that, I don't know, let's say that the value of A is much smaller than the value of A, okay? It's really long and really thin. What's gonna happen? I'm not gonna waste a lot of energy. Okay, my strain gauge would not hit the device, the phone. Okay, you know the feeling that you talk with the phone a lot of the time, talk, and it's really hot. What's happened? This stuff. The phone actually had enough time to throw to space a lot of joules, and it threw it, and some of the materials of the phone actually accumulate this joule. Oh, 3 joule, I'm gonna take it. Oh, 3 joule, I'm gonna take it. And it's become hot. That's what happened, okay? So if I'm gonna design it smart, it's not gonna throw a lot of joules to the air. The device will not heat. If, for example, I wanna measure, I don't know, something that's really sensitive to heat, I know some cell or tissue, or I don't know, which faculties you are, I don't know, but so you need to take care of that idea. You understand it? Perfect, really, really good, okay? Let's dive to the new question, okay? So the new question is a little bit more challenging, okay? This one was, a little bit to have the feeling, kind of a lecture. This, but I think it's important, right? I think right now you have more intuition than in the lecture, right? Perfect. So the next question is more like exam question, more like homework question, really hard one. And what I'm gonna do, I'm gonna, as always, fuck up the equation. I'm gonna put a really hard term in the equation, and you need to think, okay, how can I crack that and move around it, okay? So that's the idea. So the question is this. Now I'm gonna have only 2 resistors, okay? Pretty simple question. As it's seen, you have some battery, which I bought. I know it, I buy it, it's my battery, I know it. And I have 2 resistors. The first one is a cube. And the second one is kind of a cone, a really weird shaped cone, going like this. Okay? So I have, let's call it our cube, and we have our cone. We have these 2 resistors in the system. Okay? So what is the resistance of this device? They both are going to give you another information. This length is L, this length is L. They both made of the same material, rho. Okay? So what is the formula for resistors? Is what?
Length multiplied by
length.
resistivity divided by the cross section.
What is the cross section?
A.
But here in this question, this is a perfect cube. Elsewhere perfect. That's what I want you to see. Okay, they can give you 1 unit and you can actually deal with it. So this term is actually rho multiplied by L. And I want you to see the units.
No,
What? Divided by L. You are smart guy. So divided by L. So what are the units of everything here? So the unit of a resistor is ohm. Okay, you see it? It's a new unit. It's how much I want to make your life hard for the charge to press on. That's the idea. Okay. And what is the unit of resistivity? Resistivity is something that you need to measure. Okay, you put some metal rod, for example, and you measure it. So the unit of it is actually ohm multiplied by meter. Okay, I just want you to know that because I think it's a strange unit. It's like, you know what the resistance, but you need to fix it with the length. Okay, so I want you to know this is a little bit complicated. Okay, and something that I didn't tell you is that you also know the geometry of this circle. Okay, and the geometry is the radius. Okay, is equal to L, and you see that it's a kind of decay. You see it? It's decaying, right? You see it's dying out. So this radius is actually equal to E minus X divided by L, and this is a function of X because I said that this line is actually X. Here is 0, here is L.
Shouldn't the radius be half the length? Because
no, it's whatever I want. It's the length, this dimension. It's going to be 4 times the length, the radius. It's not related to the other one. Okay, so now I want to ask you what is the resistance? Okay, this was the first question. First question was second question. 2A was to find what is this term. And now I want you to find what is the resistance of the cone. So what is the formula? Not you because you're always shouting that and don't give the opportunity to the rest, which is good. So you would remember it, they don't, but let's give them a chance also. And what is the formula of resistance? L, which is the length and, okay, the length. And what is the, what here? Resistivity, which is the same for the cone. And what we have here? The cross section. What's happened to the cross section? It's getting smaller, okay? So, and with formula we have, it was just for rectangular, resistance. So we actually have here some change in A, and that's usually the question in resistors, okay? Okay, resistor, this one is changing, this one is changing, this one. First question, this was. Second question, this was homework, probably this one. Okay, so this is the idea, okay? So A is actually changing, okay? So I need to find a way, how can I overcome this challenge? So let's, remember that we had a wire, charge wire, and want to accumulate the charge inside the wire. What we did to the wire to simplify it? We cut it, right? Instead of talking about Q, we talked about DQ. Each one of them was a piece. So if I see something complicated, what I'm gonna do to it? I'm gonna cut it to its subunits and hope that they're gonna see something easier. That's what I want you to do in the homework as well, okay? Perfect. So I'm going back to this board. So if I'm gonna take this cone, let's do only the cone. So here's the cone. Oh, this we said it's X. And hop, hop. And you see that the charge is actually coming to it. They say, oh, I'm so lucky, I have so much space, I like it. I like to be here, I don't have a lot of resistance. But as they go along here, they said, oh my God, this road have a limited passes to go by. So this resistance maybe is different than the one at the beginning, right? X equals 0, and here X equal to L, right? Sorry, L is this. X between 0 and L. You see it? This one. Okay, so let's draw this kind of thing. How it look like? It's kind of a, if I cut it, you know, it's kind of like a coin. You see it? I can take a lot of coins and put it in a row, and then eventually they're going to have coin, right? So let's ask what is actually, let's call it dr because it's a small resistors, okay, dr of this coin. So what is the length of the coin?
Dx.
Exactly, it's dx, okay? So I look at the form, I said, I know you are dx. What is the material property of this coin? All the coins are the same. There's no different thing, but think about it, I can do a trick. What I can do, I can actually wet this part, right? Or have a function of wetting this thing, or think about it, how you say it, when you put copper outside and you get oxygen, you know this process?
Rust.
Rust, exactly.
Corrosion.
So if I have corrosion, rust, right? So I can have, for example, at the outside, at the radial direction, a different material than in the middle, right? So that can happen, okay? So in our case, it's easy. It's just row. And what is the area? Is R, exactly. But it's a, what is this area is? It's a circle.
R squared.
Exactly, that's what I want to hear. And it's a function of x, right? So we actually succeeding understand how looks the resistors in location x. You see it? Perfect. Because the world is not perfect. The world is not about cubes or rectangulars. The world is more about like this kind of shit, right? And you need to know how to take shit and make it beautiful. That's the idea of being engineer, okay? So I'm gonna clean this one. So I wanna ask you how these resistors actually connect to each other, all these coins. So if I'm gonna take, this is the first coin, right? And it's connected to the battery, right? And this one is connecting to the what? The second one. And this connect to the second one, and this connect to the second one, and this connect to the second one, and this connect to this connect to this, right? So what kind of this? It's in series, right? Why it's in series? How did you notice it?
It's connected by the same wire.
One way to say it is the current is all the way the same. It's uniform. It's a way to look at it. But how I like to see it is saying I give this energy, and they all fighting who is gonna get more energy. How can I see it? For example, the energy in this one is VIR, right? And R is changing by X. You see it? So each one gonna get a different amount of energy eventually, right? You see it? Because R is changing. I don't know how, but it's changing. Probably if A is actually in here, and A is getting smaller, so this thing getting bigger. So I'm expecting this part to be more consuming, right? More energy, right? Because the resistance, in the opposite way. A is actually getting smaller, so resistance is actually getting higher. So this one gonna ask for more energy, right? They're gonna get more energy, okay? And throw the energy to the wall, right? So that's the idea. So good for you to understand. So what is the equivalent resistors? We know that R con equal to the sum of all dr, and I see in the audience people shouting with a lot of passion, that if we actually have this really a lot of small units, we can make this one integral, right? So this is a dr. And what are the limits? I don't know to say it in this language. I need to change language, but I know the dr is equal to what? 2 rho dx divided by pi r squared, and r squared is this kind of monster, right? This is a monster. Exponent, but we are engineers and our job is to kill monsters, right? That's the reason we had math class, okay? So, and now in this language, I know how to present the accumulation of resistors. I'm starting where? At 0. At 0, exactly, and end up at? Perfect, that's it, okay? So we need to do this integral. I'm going back to you. No, I'm going back to here. Cameraman, follow me. So eventually, what I'm gonna get is that R cone, which is what is the R total, not R total, sorry. R cone, which is the integral is actually equal to rho divided by L, the square minus 1 divided by 2 pi. Okay? Good? You see it? So what is the total resistance of the circuit? They are two connected to in series as well. So R total is equal to this thing plus this thing. So it's rho 0 L exponent minus 1 2 pi minus plus 1. Okay? That's the idea. Perfect? Got the idea? So what's really interesting usually in circuits is what is the current. That's what most of if you're getting the voltage, probably they're gonna ask for the current. If you have the current, they're probably gonna ask for the voltage. Usually that's how it goes. And the resistance, you need to calculate by yourself. Usually that's the kind of questions. Okay? V equal what? IR, which is the V load, okay? And I equal to the voltage divided by this kind of thing, right? So, bye-bye. See you soon. Okay? And this term is actually ending up to be, I'm cleaning this one. Camera, you see me? Perfect. So this one end up to be, and I equal to 2 pi V0L divided by rho 0, 2 pi exponent plus minus 1. Good? Now I want to ask you a new concept, a new question is what happening? You know, current is a general term, right? Is how much current is going in a second. If I have a pipe, okay, you're following me? You with me? Okay, I'm gonna explain it later if you need. Okay? So if I have a pipe, okay, with some water, okay, right now I'm watering the garden, okay? And what's happened when I take my tongue and close and put resistance, right? The most I can do infinite resistor, which are gonna block, obstruct all the way out, which is like the wood, it stopped the current, nothing, right? But I can also not put it all the way. What's happened to the flow? It was slow, and then when we threw the finger, what's happening to it? It's become stronger, it's become fast. So what I want you to see is, if you're thinking about it, that you have this eye, here inside this thing, what I expect it to be, I expect to see that the charge, look at the charge is going here. Okay, let's say do it, visible. So if this is, the cone, so the charge going inside this stuff, and here they are happy, they are spaced from each other, you have plenty of room. By the way, you and I are kind of resistors. We actually drawing energy to the environment of around 100 watts. Okay, that's the joules. Okay, in each second you throw 100 joules. So that's the reason when you enter a room And there's a lot of people say, well, dude, it's really hot here. Why? Because there are a lot of people, each one is 100 watt. And lamp is 50 watt, okay? So you can think about that it's about full energy. The reason that when you touch a lamp, it's not that hot, it's super hot compared to touch somebody. It's hot if you touch somebody, you can feel it. But it's not that hot, it's because we have a lot of surface area, right? Actually, accumulates from every place, yeah.
So we have resistivity. You calculate the resistivity.
Yes, I can definitely measure the resistivity if I want to electrify you. Okay, I want to electrify you, so I can actually measure your resistivity. And guess what? Blood have a different resistivity. Skin have a different resistivity. Skin, okay, skin in the hands actually have 10,000 scoops. You are really protected, okay? I need to apply a lot of voltage to get you electrified, okay? A tunnel light or from, from the wall, from the power station, okay? So that's actually your skin resistance, okay? So let's go back to this idea. So what's happened to the charge when they go in here? Dude, I feel hot, there's a lot of people here, I'm dense, right, to see it? So actually what I want to talk about right now is something that's called a current density. Remember that we talked about the charge density? We have like Q is equal to the integral of sigma, which sigma was a coulomb per meter square, right? Multiplied by dA. So right now I want to do the same thing with the current, okay? I is equal to what? To integral J dA, okay? So, and another concept that I want you to see, that the direction is matter, is changing the game. So we actually have here, this one is a vector, and this one is a vector. How you can think about that if I'm inside, the ampermeter, right? And I'm standing to count charge, and hello to you, positive charge, come along. Have one positive charge that pass by, hey, hello, positive charge, come by, second, and then a negative charge go that way, right? Sorry, negative charge go that way. So, oh, it's a negative charge, I need to subtract because you're gonna cancel some of the positive, right? So the direction where you go and what charge do you have actually matters. So this one is a vector, okay? So dot dA. So what actually happening, so this is called the charge, the current density. And the current in general is stupid. Okay, it's not smart, it's actually, it's Coulomb per second, but the charge density actually Coulomb per second per the window that you try to pull it inside meter squared, okay? See? So I just gonna finish with that. So we actually can calculate what is the current density. So let's do this one. So the current density is actually I equal to J dA, and this is true for every section. Every dx have some A, right? And have the same J. This is J entering this area, okay? And this is J entering the area, and J don't have any preferences to go anywhere. It's the same at each X is the same, okay? So J is going outside. So J integral dA, this one is AX. And then I get the J, which is kind of an obvious answer, is I divided by how much dense I feel, and it's a vector. So in our case, it's the X direction if the cone is really low. Okay, so did you understand this term? Okay, here, usually it's gonna be that way, that I divided by A gonna give you J. Okay, in a more advanced classes, you're actually gonna have a different thing. And what I wanted to say, since you have a class right now, yes, okay. So what I wanted to say to you is, we almost finished electricity. You have the RC circuit, right? We're gonna cover that in the lecture. And we're gonna take capacitor and gonna take resistor and put them together. We're gonna see what's going on there. And right now we are moving to new subject, which is called magnetics, okay? And I hear that a lot of people say, dude, the homework is really hard. It's really hard for us. And I want to say something that's gonna be really nice for you to hear, which is from now on, the class is become super easy because you learn electricity, and to be honest with you, you don't know electricity because if you don't understand magnetism, you actually don't understand electricity because they are so connected to each other, which is called one phenomenon, electromagnetism. And right now we're gonna start a new page, a fresh start, and we're gonna study again everything that you already know. For example, you learn Coulomb's law, right? For a charge, for force on charge. So you have Lorentz law, which is the Coulomb law of the magnetic. So it's gonna be really similar. And you learn Gauss's law. You're gonna learn the Gauss's law of the magnetic. And you learn this thing, and capacitor, you have the kind of a capacitor of magnetism. So actually the class gonna repeat itself from a new angle of view. And this also gonna enrich you with new knowledge, but also gonna make the old stuff getting better. So the class from now on should be easier for you, and this is such a relief. You know why? Because the end of the semester, really tense, a lot of classes, you know, a lot of homework, a lot of exams. So this is actually a really cool thing about this class. So at the middle, it's actually shift itself to a more easy way. And actually, I'm gonna say, you don't learn 50% of the class, you actually learn more because you actually learn the concept of the class, which was the hard part of the class. I think Gauss's law was the hardest. Okay, Rafael, thank you very much. Thank you guys for joining. I'm gonna see you in the next time. You have more questions about resistance in the YouTube channel, okay? So check them out. I'm gonna take care of the resistivity. Resistivity gonna change in space, which is more related to the homework, okay? Perfect, see you soon, and good luck. I'm gonna stop the video. Nomi, you have a question? Perfect. Okay, perfect. End.